So next up, we've got Dr. Helen Hasenfuss. So Helen completed her, Helen completed her PhD in interactive interface design in 2018 and continues her explorations as an independent researcher and multidisciplinary designer. Her study included investigating the potential of smart and non-Newtonian fluids, biomimicry, 3D modeling, and prototyping in order to design a programmable technology for a more significant and direct user experience. Exploring the challenges of shape-shifting technology highlights the interwoven nature of creativity and logic. So I'll hand you over now to Helen to deliver her talk, which is entitled Shape-Shifting Technology, Transforming Science Fiction into Reality.
Perfect. Thank you very much. And first of all, thanks for the opportunity to present for this festival. So I'm going to launch straight into it. Oh, yeah, I should share the screen first, actually. Sorry. All right. Already getting carried away. Okay, so essentially, my area of research is in shape-shifting technology. And particularly, there's a specific gap that I was looking into. So starting off with, say, the quotation that you can see there from Aristotle, the whole is greater than the sum of the parts. So imagine you have an artificial system that's made up of many small uniform parts or agents that work together to create a larger whole. So for example, if I wanted a specific tool like a wrench, that I could give this command to these agents, they'd communicate with each other, they'd self-assemble into the tool, and then I'd be able to use it. Or for example, if these agents were scaled to a smaller level, so for example, on the micro or the nano scale, that we could use them to create computer interfaces, such as a keyboard or computer mouse, or even an entire system like a mixing desk, for example. So a question that might come up is this technology even realistic? Is it even possible? And I think we only need to look to our main source of inspiration for a lot of technological developments, and that's nature. So I'm pretty sure everyone is familiar with ant or termite colonies, or even beehives. So these are perfect examples of multi-agent systems, of many agents communicating with each other and building structures larger than themselves. So for the initial origins of my own research, I looked to fire ants. And in particular, these ants, because they not only in normal circumstances can use materials from their environment to build their structures, but also in times of an emergency, as you can see on the left-hand picture there, in times of a flood, they use themselves as the building block in order to create the structure for them to survive. So in this case, like a raft. So you can see from the picture there, it's a very organic shape, very fluid, and of course it serves the purpose that they need. But for structures that we're looking to maybe create with shape-shifting technology, we need an agent design that's a little bit more suited to our requirements. So that's exactly the gap that I was focusing in on in my research. So there have been two main aspects into shape-shifting technology, and that's the communication between agents and then the actual process of self-assembly. So just starting, what we have in reality, what already exists is, for example, a project like this. This is called Kilobot. And to the time of my study, it was the largest group. So there were 1,024 of these little agents that could communicate with each other. And as you can see, once the user gave them the command to create, in this case, a star shape, they would self-organize into this shape. So they can communicate with each other and to a degree interact with the environment around them. Now, whilst this is a very big step forward, this is self-organization. But what we need is self-assembly. So we need them to be able to build 3D structures by themselves. So this was the other large aspect in the area of shape-shifting technology. So the self-assembling process. And the main shape that was used for that is the cube. So I'll get to that a little bit more later. So the other aspect for this project, which was quite interesting, is not only working with what exists already and what is a tangible progress that we can make, but also because we don't have a final application for shape-shifting technology, we need to incorporate a bit of creativity and our imagination. So I found these two examples, and I found it very interesting that in film, they're beginning to experiment more and more with what this type of technology can do, how it can look like, and what we would like it to be able to do. So for example, on the left-hand side, there is from the animation Big Hero 6, and that structure was called Megabot. And yes, I did recreate it, and no, it doesn't work because its fundamental functioning is based on magnetism. So even if you use electromagnets, with that proximity of that structure, you're going to get magnetic interference. So you can see imagination is great for the idea, but in reality, we still need to tweak it a bit. So the shape on the right is again from the film Transformers, where they have the same process. Many small robots working together to create a larger whole. Now you might think the process on the right is the design is extremely complex. But again, if you look to nature, it's already been there essentially and done that. So this example is of a bacteriophage virus. So you can see the structure that is possible already in nature, and that on a nanoscale. So it kind of gives us the scope of where we are and where we can basically aim for. So again, the self-assembling process has been a major part of exploration as well. And the cube has been the go-to structure, which is understandable and which makes sense. We're familiar with it from a very young age, and it essentially permeates through our society and our knowledge. So I didn't stray too far from the category in which the cube is. Instead, I chose a different starting point. So I chose the dodecahedron. The dodecahedron is semi-spherical, and it has 12 facets, so 12 sides instead of 6. And this was the core, basically design, the starting shape. So then cutting a long 5-year story short, the research that I carried out, I basically came up with these 7 design parameters that I proposed would influence a better design, an agent design, that would be more suitable for the applications that we would need as people. So there you have the semi-spherical shape. You have an irregular cratered surface, which means that the agent itself, the individual agent, can change its structure. You have autonomy relates to the communication and being able to survive in the environment. Scalability, as I said at the start, to be able to go to the nanoscale if possible. The ability to assemble and disassemble, meaning that it can be reused and form different shapes. Behavioral simplicity, this again leads to the communication, but also the consideration of artificial intelligence algorithms. And then bidirectionality, which is a unique quality of our own haptic sense, so our sense of touch. So essentially being able to affect the environment, but have the environment affect us as well. So as I said, the design I started with was the dodecahedron, and I created the dot. So yes, the name isn't very creative, but when you've written it a couple of hundred times, you appreciate something short. So what I envisioned on top of the dodecahedron, so just in case anyone isn't sure, the little pink, this shape, this is essentially the dodecahedron. And what I envisioned is that from each facet, there's an arm that can extend and retract. So that was the main idea. So that again starts to fulfill some of the criteria of the design parameters that I had come across through the research. So it can change its surface topology, and then through a process of experiments, I tried to postulate and stipulate whether the characteristics would succeed. So rather than creating a fully fledged prototype, because they have a tendency to just stay in a lab setting, I just simulated the behavior. So in this example, it's the self-assembly or disassembly behavior replicated through 3mm ball magnets. And others experiments include whether the shape can scale. Towards the end of the study, what I wanted to do was illustrate the shape and how it can work. So basically, this is a 2D profile of the dough